Okay, so now we move to the second talk of today by Hyung Do Kim from Seoul National University about the weak scale as a trigger. Please, Hyung Do.
Thank you. I think I already gave a talk in Newton seminar, so some of you are familiar with the topics, but this time I will use the Blackboard, so you will get a better delivery this time. So can you change it to the Blackboard? Yeah. So I mean, if it goes well, at the end I will show a few slides and for your help. But I found that it's more difficult to deliver the simple idea with the slides, even though it's a lot easier in Blackboard. So this time I will use Blackboard. So this is a work with Nima and Rafael for 3, 4, 5 years, and it has been delayed so many years, but still eventually it was finished. So the weak scale as a trigger, the weak scale came from an idea that we have the most notorious problems, the cosmological constant and the gauge hierarchy, and whether there is any connection between them. I think this became a trend in recent years, and this is one of the new ideas that connects these two coincidences. So you can imagine the universe where small cosmological constant is possible only when the weak scale is the value that we observe now. So the story goes to realize this idea, whether we can invent the setup where very special weak scale allows the small cosmological constant. Otherwise, CC is always big or negative, and you never has a universe with a long life. So for this, I just define my convention. This is the cutoff of gravity. You might think it's Planck, but we are dealing with many degrees of freedom. Then in principle, it can be lowered by the degrees of freedom. So it can be very low. And then there is an independent one, Higgs sector. So also in the sum model, the cutoff is Planck scale, but you can imagine SUSY or composite Higgs or whatever UV completion of the Higgs sector, which has nothing to do with the gravity. So lambda H could be lower than M star in principle. And then we have the 2 basic questions. And Planck to the 4th, and then Higgs mass square, 10 to minus 30. And so the simple anthropic or the landscape picture is that if we have 10 to 150 vacua, so these are number of vacua in UV, and then just randomly scan CC and Higgs mass, there would be one vacuum whose CC is tiny enough by this amount, and weak scale is also small enough. Or any particular combination which is of UV vacua can be realized in this landscape. But imagine that for some reason, this number is smaller. So even though you allow random scanning of 2 relevant operators, you will never get the universe with a small CC and small Higgs mass. So that's an assumption. So once you accept this, and then I will consider UV landscape, which is given by these. And then there would be lambda UV, which is the smallest CC in these landscapes. So I don't assume anything about the landscape picture. So CC can scan any value. And then this is the most natural one. And the number of vectors just determines the smallest possible CC in this landscape. And roughly, I mean, in order to get a feeling for you, you can imagine that this is the weak scale to the fourth. And of course, this is much bigger than CC that we observed. And then there is another infrared physics where this lambda UV will bring down by IL physics. And this number of IL scanning would be 2 to the n phi, where n phi is number of light fields phi i's. And phi i's are in such a way that each phi I has an exact G2 symmetry. So this is just a toy illustration for this mechanism, but you can also use your own favorite actions or whatever. So you imagine some tiny breaking of shift symmetry for this pseudo-Goldstone boson. So epsilon is a breaking of this, and then G2 is preserved. So this is the simple potential that you can imagine for V over phi I. So when this is the potential, basically they don't play any role for scanning CC because these two vectors are exactly degenerate. However, you can imagine some special trigger, let's say OH, and then couple it with phi. So the linear term for the phi potential arises from, let's say, kappa I and some epsilon I, because it comes with it. And then this linear term actually lifts up the degeneracy of the potential. So you will get a different minimum, different potential energy for two different minima. And then they will provide you the extra scanning of the cosmological constant. I told you that there are n phi of these vector. So actually, in the beginning, there are 2 to the n phi degenerate vector. And then each vector are lifted up like this. And then there are 2 to the n phi scanning of the cosmological constant possible in this picture. So,
excuse me,
yeah.
I have a question. So you're scanning the Higgs mass in the UV?
Yeah, in the UV, the cosmological
and yeah,
both does
but
scanning. Yeah.
you don't want to scan also the parameter of these other scalar fields?
Oh, this is the pseudo-Goldstone boson, whose mass is extremely tiny.
Yeah,
and
but this,
that shift symmetry is governed by tiny parameter epsilon. Yeah.
But don't this the parameter of this effective potential? Yeah.
Yeah, I mean, I think order one, let's say there is a phi square and phi to the fourth, and each one comes with order one coefficient. That doesn't affect the conclusion.
Okay, but in principle, you would expect also a landscape for those parameters.
Yeah.
Why are they different from the Higgs mass? And then the number of agua will be much bigger.
How can I say? So first of all, you can really separate the UV landscape and IR landscape. So UV landscape, all those capital Phi's are taking the web of M star, and then also the mass of these fields are of order M star, if there is no special reason. So everything is at M star. So I integrate it out, and then I'm wrapped with the theory with the very light fields. So these are the fields even lighter than the weak scale. So it is still there. And then all the questions that I'm talking about would be just the consequence of the UV landscape. So you can understand that I fixed my CC and fixed mass, and then for that landscape there might be some fixed value of Ordon coefficients here too, but I don't care. It's just a tiny.
But the total number of vacuum will be much bigger than 10 to the 150, or?
Oh, no. Just the total number of UV vector are less than 10 to 150. That's the basic assumption.
Yeah, I don't fully understand. Maybe we can discuss later.
Okay, perhaps I misunderstood the question. And yeah.
Hyung Do, connecting to the question by Giovanni, the way I understood these things is that this is kind of a friendly landscape, to use the technical word, in the sense that only the Higgs mass, for instance, scans, whereas those parameters set by some marginal dynamics, so not some super renormalizable dynamics, that is essentially fixed. So for instance, this M star could be the confinement scale of some dark gauge group, which does not scan in the landscape because there are explicit constructions in which only dimension full quantities scan, dimensionless quantities scan only logarithm. I mean, very mildly. I think that this is what
thanks
you
for the
have in mind.
explanation. So that is true in the star model, and then we introduced this new light scalar particles. So his question was about another dimension full parameters, why they are not scanning. And then I'm just answering that there might be some number that was given for given scanning of the CC and Higgs mass, but doesn't matter as long as it keeps G2 and it is tiny enough. That's
Just a final comment. I mean, for me, it's a little bit hard to believe that in a fundamental theory, some parameters scan and some don't. But okay, this is
you mean
maybe
why the dimensionless couplings are not scanning?
Eventually, even the dimensionless, because what you call dimensionless, a dimensionful is your choice. I can say the lambda QCD is my dimensionful fundamental parameter instead of alpha strong, or the web of the moduli.
It is given by the dynamical dimensional transmutation, right? So once you have
no, I can
UV
define my theory. I can define QCD by giving lambda QCD, not alpha strong. Or alpha strong at which scale?
What do you mean? You can find it.
Okay, we can discuss about field theory.
Yeah, but I'm just thinking of the standard picture where you start with the gauge couplings and run down and get lambda QCD. And then this lambda QCD is also a function of the weak scale because it depends on the quark masses. So in this picture, there is a UV landscape and then the landscape which is given. So in principle, this depending on whether it's E2 to the N5 vacuum are degenerate or not, they can play a role of extra scanning of CC. And the crucial idea is basically it works for very special value of the weak scale. So if the weak scale is in between two values, then this lift up of the potential is possible. And then this extra scanning works, and then you end up with a universe with a very small C. Otherwise, no extra scanning, and yeah, you just end up with a huge CC universe, no matter what the weak scale is. So in order for this mechanism to work, I think of the triggering operator. Which can lift up this potential. So the easiest one that you can imagine is, of course, the Higgs operator. Right? But we all know that there is a hierarchy problem in the cell model. So let's say I write down the potential like this. And then this is not the observed Higgs mass because the loop correction coming from, let's say, this gives something like this as a cutoff dependent contribution. Also, if you close the loop, then you will obtain of order this contribution to the potential energy. And then these combination will determine the physical Higgs mass. So I want to find the setup where the operator just directly depends on this physical Higgs mass square. Nevertheless, once you write down this h dagger h, then you can, let's say, I can imagine extremely light field phi, and then couple it with the h dagger h. Then there is a loop diagram that is quadratically divergent. So I just end up with something like this, similar to this. So even though the weak scale is very tiny, always this operator is dominated by the UV physics. So in other words, you can say that the expectation value of this operator, OH, is actually divergent in the Snell model. So you need some theory, some setup where this quadratic divergence doesn't appear. And in the Snell model, there is only one example. Yeah.
If the Higgs was composite, then this will become a trigger as well.
Higgs is what?
If the Higgs was composite.
Composite. Composite means your cutoff is low, right?
Yeah.
That's it, right?
Mm-hmm.
So if it is just at the same level, then you can barely use it. I mean, it's marginal, meaning that we don't have a hierarchy problem. So you just have a new physics scale, and then weak scale is predicted to be there, and that's it. But we already know that we have a fine-tuning problem in the Higgs sector. So basically, that fine-tuning problem is encoded here as how indirect this trigger is to the Higgs mass, right? So if you accept it, then in the Snell model, this is the only operator. And then, however, this is nothing but the derivative. And we know that if you couple it phi to the total derivative, this is nothing but the this interaction. So it doesn't contribute to phi. I mean, you can remove it. So basically, there is no expectation value for this. Except that there is a non-perturbative instantaneous effects, which provides you interesting potential, of course, in the presence of zeta, and then can easily extend the argument that if you couple seed phi to this operator, then basically it's a shift of zeta, and then there is a extra term entering here. And from here, you can find that there is a linear term in phi. Psi. So basically, this is the operator GG dual. So there is one example where all these values has dependence on the weak scale. Therefore, using that weak scale dependence, you can trigger GG dual operator as a trigger. Nevertheless, the size of this, even multiplying by zeta, is already too tiny, at most 100 kb to the fourth, and there is a very limited room when you play the game with this operator. So I will not discuss it now. Instead, I'm going with the second operator in Twix-Doppler model. So in the Snell model, there is no operator satisfying my criterion because you can imagine, let's say, the Yugawa operator. since this get a wave and then there is a QCD condensates. So you might naively think that there is a free lambda QCD to the cube contributing as a trigger. Nevertheless, you end up with the same problem when you couple it with the phi, because the phi, let's say, so the standard Yuga coupling and the presence of extra interaction with phi just generates the loop of QC and Higgs. So this is two loops, and then these are quartic divergence diagram, and you also have the same problem. So basically, all these operators, if it is present in the Snell model interaction, then you cannot use it. But in the Snell model, there is no exception. Any operator that is allowed by the symmetry is there. Therefore, there's no operator that is available, except the massless upquark solution. If it was realized, then we could use those up Yugawa, which is not present in the Snell model, and could work with this, but that's not available option these days. And therefore, we should go to BSM for this purpose. So I take the first simple example, BSM example, 2 Higgs doublet. But this is what is called type 0. Just like this model, if you allow this operator without phi in your Lagrangian, then you have the same problem, right? You close the loop of phi and generate the tadpole dominated by something else. So you have to forbid it. So phi b mu generates plus b mu here. And therefore, once you try to use this as the trigger, then b mu, if it is present, should be less than v squared times 16 pi squared. So here, I assume that it is 0 completely from the beginning. But I mean, tiny b mu term doesn't affect the conclusion. So in order to make this mechanism to work, I impose G2 symmetry. So under this G2, phi goes to minus phi, and then H1, H2 going to minus H1, H2. So B mu is forbidden by this G2. And if you combine this G2 with the U1Y gauge G, then actually you can rotate using hypercharge and assign many different charges to H1 and H2. So there is a subgroup, which is G4, under which each one carries G4 charge 1. And then the interaction of the Yugawa is of this one. So QUC carries minus I charge, and QDC I, ADC I. So these are kind of G4 charge assignment. And then you can also easily notice that this is not the only option. As I told you that, although the standard Yugawa is not allowed, in order not to have flavor changing neutral currents or all the problems, I only use this H2 coupled to fermions. And then H1, Yuga couplings are not present. Therefore, I can use H1, for instance, as another trigger. However, the scale is always much suppressed compared to this. So this is not the best option that I'm using here. And then, so in the standard 2x doubler model Lagrangian, which I will not write down here, but there is a B mu, and then lambda 5, lambda 6, lambda 7. So the standard mixed quadratic, but this is something like H1 square and H2 square. And then this is, 6 is, and then this is H1, H2 square. So I don't allow, so this is odd under this G2. So all these are forbidden like B mu, but lambda 5 is allowed because minus square is even. So this is allowed by G2. So, and this is really crucial to increase, to give a mass to the charged Higgs and also the CPR Higgs. So you can easily see that compared to the standard 2x doubler model, where this B mu term actually allows you to have this decoupling limit, here that's impossible. So there are only two mass parameters, the mass of H1 and mass of H2, and each one should develop its own BEV. And then basically their scale is constrained to be the weak scale. So they cannot be heavier than the weak scale. So it is really tied to the weak scale, and phenomenology is really suffering. And this lambda 5 is saving the charged Higgs and CPR Higgs from being excluded. Then basically I can draw a picture. Type 1, regarding Yugawa couplings, the same, but we call it type 0 because there is no B mu. So it's a special parameter space of type 1 2x doubler model. You can understand it that way. And then let's say I can call this mu square as the expectation value of OH, which is V1, V2. And then in terms of mu square, you can think of cosmological constant, and then there might be some minimum value allowed by lambda UV, and then only in this particular range, your small cc is possible. So how is it possible? The idea is extremely simple. Let me start from the UV picture. So in the UV landscape, there are scanning of CC. So 0 is somewhere here. And then the nearest smallest CC is far from 0. And this is the UV landscape. And then basically, you can start to turn on the weak scale. So if this is the case where mu is equal to 0, and then mu is very small, and then your each VQR has 2 to the n phi degeneracy, and then they are repeated up, but not by a huge amount. They are just in the vicinity of each one. Because now the splitting is, in this case, when mu is less than V, much less than this lambda UV. And then when you increase it, eventually the splitting would be sizable enough, so it can fill up the gap between 2 CC. And then basically you can, in the vicinity of 0 cosmological constant, you can find the smallest CC, which is lowered by lambda UV over and IR. And then you can continue. So this is the region where mu S is determined. So before you reach μs, even though this 2 to the n5 degeneracy is lifted up, basically you never touch nearly vanishing cosmological constant. So it's useless. And only when you fill up the gap, they start to be relevant. And then basically, even the size, I mean, the splitting could be much bigger than lambda UV. So the splitting would be this way from the first one, and then the other way from the second one. We have a nice figure with the different colors in the paper. And then anyway, filling the gap would be the same. So this will continue till the point where catastrophe happens that in the previous talk already it was used. And so if the tilting is too much, then you lose the second minima, right? And therefore you end up with a single vacuum for each phi, and there's no degeneracy left. So it's just you are going back to a setup where, although picture is the same, here are 2 to the n phi degenerate vacua. Here is just a single vacuum. So you have just end up with a large EC like this with a different interpretation. So only in between these two regions, basically this mechanism works. Yep, sure.
There's only one of the Higgs is coupled to the standard model fields.
Yes.
So what happens if the web of that Higgs is very small and the other is very large? Because you're constraining the product of the two webs.
Yeah, so I don't have, yeah, so I think I can skip all those details of the computation, whether you can find the consistent parameter space that is compatible with this. But in order to answer your question directly, basically, I can imagine the charge-Higgs mass and then CP even Higgs mass as a parameter space and can look for the allowed parameter space. So basically, we looked for all possible parameter space, and the philosophy is basically V1 should be much smaller than V2 because we know that the Higgs that we observe is very similar to the sum-model Higgs. So it's the one that mostly coupled to the gauge boson that couples to the fermions.
What does that mean?
So it means that even though you have two Higgses, so the one that couples to the fermions and gives a mass to the fermions are the one that is taking most of the webs. And then the other Higgs that we introduced has a very tiny web, tiny meaning that it is about 1/3 or...
Sorry, why can't I have the opposite? What excludes in your reasoning the opposite situation where the web of the Higgs in that couples to our fermions is so small so that it's only broken by QCD effect?
And then you have to explain those production cross-section of this H1. Which
Forget
is like,
about phenomenology. I'm talking
forget
about
phenomenology.
the consistency of the theory.
I think this conclusion came out spending lots of time trying to figure out the allowed parameter space of Higgs searches.
What does that mean? But you cannot apply Higgs searches at this point. The prediction, there is large part of the parameter space where the prediction of the model is that the Higgs wave is small and also the cosmological constant is small. In fact, the Higgs wave can be so small that it's only brought by QCD. How do you exclude in those vacua?
You're saying, forget about our universe. And just in this picture, what's wrong with the W and G bosons?
Because I don't know. I mean, the rules of the game that I've been hearing so far have been half anthropic, half bedtime story, half trying to make self-consistent arguments. So what do you keep fixed? I mean, you can be shifting around, but one of the prediction is that you have tons of vacua where the electroweak symmetry, the fermions are only getting their mass from the breaking of electroweak due to QCD.
I think what I can tell you right now is basically, so this is given by your setup, right? Let's say your potential height determines mu b. So I just chose, so this initial potential for phi has this shape. So this height is nothing but epsilon square m star to the fourth. And that determines what is the largest possible kappa epsilon phi. So phi is m star and the weak scale square. So mu b is determined if those potential height is determined. So it's a kind of starting point. So I choose this to be the weak scale. And then for this one, also this lambda UV determines mu s. So depending on my UV number of vector, basically.
I don't know why this, because didn't you define?
So just imagine that there is a universe where the setup was given like this. And then in this universe, these two Higgses can take a value only in between these, which provides you the small CC. Otherwise, CC would be big. That's all.
But how in the what you explained then? Okay, perhaps
So
we
this
can
is
describe
just
later, because what mu is you defined as V1 times V2.
Yeah. But that mu is needs to be in the window.
Oh yes.
And this window is set by my setup, which is independent of the star model. One is from the phi potential height, and the other is coming from the UVCC.
Maybe you're not answering my question. There are vacua the way you're describing here, where in the middle column, I have a small cosmological constant at the value that's measured, but the Higgs wave is tiny.
Oh, yeah. I think there would be a universe like that, which is allowed by this picture.
Yeah,
but
why are we
that's
not living there?
Why we are not living there? I think it's a half and half chance.
Oh no, but this is a measure issue. Again, we are making up bedtime stories to explain this whole reasoning. I don't understand it's half and half chance. You're putting a measure, you're assigning probability to what your landscape, how it is populated. How do you know? Did you calculate it?
I mean, I'm not saying that this, so there are very limited range of this parameter space that is consistent with our
Forget
searches.
about, it doesn't matter. There is,
then
forget
this
about our
picture just
universe.
tells me that the weak scale should be in between, that's all.
Exactly, so you're constraining just the product.
My
Forget
prediction
about,
is that's all. Right.
exactly. So
Yeah.
you're constraining the product of the two waves, right?
Yeah, correct.
Okay.
Yeah. And then the last constraints comes from those kappa, epsilon, m star phi, h1, h2. Inevitably make a loop, let's say phi I going into phi j. So if this loop is allowed, then I just end up with the kappa I, kappa j, and then epsilon square times m star square phi square. And phi square would be m star to the fourth. So inevitably, also they put a constraint on possible size of kappa. If kappa is too large, then already in this picture, this loop diagram just provides you the additional scanning, and then your UV lambda would be lowered down, and therefore, in order not to have that, kappa should be tiny. Yeah.
Sorry, there is a way to quantify my complaint. So in your case, you have one vacuum where the cosmological constant is small, but the product of the two waves has to be TV squared, whatever that is. So why does that vacuum, where the cosmological constant is small, coincides with the one where the two waves are comparable, instead of the one where the Higgs wave, the one that's responsible for the standard model masses, is tiny. So there is a tuning inherent in your logic if you want to use the weak scale as a trigger for the cosmological constant.
I think so. I think the best explanation might be provided if I can take the example where M1 square. So actually, your case is related to the case where if I allow B mu, then one get a large wave of order M star, and the other one get a wave B mu over M star. And then the product always remains as B mu. So there is a huge degeneracy that is allowed. So it is really a big problem. But in this case, actually, each one has a kind of a limit. And let's say, so why? Yeah, I think I can go to this other examples where M2 square is positive. In such a case, naively you would expect that this trigger is 0 because H2 doesn't get a wave. But we all know that this QUC condensates provides you the tadpole to the Higgs, and therefore always you end up with this size of the wave. And then there is a alternatively equivalent universe that you worry about, where the other H1 get a wave of order M star with a listed tuning, and still the product may satisfy the window that I'm talking about. And yeah, this universe is allowed. And this universe has an extremely different picture. So yeah, I should state it precisely that this explains this only explains that this trigger operator should be around the weak scale, but that's it. And then there's a caveat that one of the breaking, not M star, it's lambda H, would be maximally broken. So basically WN G boson mass is around the cutoff of the Higgs sector. And then all the fermions are extremely light. And that light fermions has a additional suppression of this compared to the central value of the weak scale. So in this picture, you can say that compared to our observed C, say lambdas, basically all these fermions, in order to form an atom, because the lepton mass is suppressed by this amount, so there should be additional vector like this. So in this universe, the CC should scan down much further to a tiny value in order for atoms to form. So that's an extra argument. So so I mean, it's up to you. You can choose atomic principle and forbid it, or you can just allow the other universe, and that's the best that I can tell. So there are two options.
Yeah, I'm sorry. I thought the rules were to just use the CC tuning, swallow the CC anthropic argument, and only use that. if you also use the atomic principle, you don't need any of this story.
No. What I'm saying is, so there are two options that you can choose. I mean, it's entirely up to you. So the prediction is A, the universe where two webs are comparable on both sides of the weak scale. And option B, the second universe where the gauge bosons are extremely heavy, but the fermions are extremely light. And the universe is, unless this is extremely tiny, it's a universe where the expands, inflates before atoms form. So that's a very, we have a universe with like us and the strange universe like this. And it's a combination of this.
If you only fix the product, there is all kinds of universes in between. You only fix the product V1 times V2, H1 times H2, right?
So what's wrong with the?
With all kinds of intermediate values.
You have an inherent tuning by the fact that your technological concept may be cancelled on by the product is small, but you have no constraint on the other. The inherent tuning is the entire mechanism. Whatever argument you use on top.
Yeah.
Basically, the mechanism doesn't work.
Yeah, I think I should admit that at the final stage, it's only the phenomenology that got rid of all those things.
Use the observed value of the Higgs mass and have a one Higgs model called the standard model.
No, but that doesn't explain.
Grazie. Well, I would say that there was some progress in this discussion, even if relatively small. So unless, Hyung Do, you would like to add something, or someone from Zoom would have any enlightening comment, I would maybe come to the conclusion of the talk, the time you need, and then we have time to keep discussing later. For
I don't have a good answer at this moment, so let me think about it. And
please go on.
I'm
Yes,
fine with the Zoom questions or whatever.
I guess is the talk over, or you wanted to add stuff?
Oh no, I'm done.
Ah, you're done.
Yeah.
Okay, that's okay.
I think I delivered everything. That's why there are really keen questions came out. And so the picture, at least what I'm claiming is there is a very limited class of the operator which can be used as a trigger. And then you can use this scanning, narrowing down the scale of the operator expectation value. So in that way, you can correlate the operator expectation value and the small cc. And the claim is whether this operator is not directly related to the weak scale, but just the product, meaning that actually the breaking of the weak scale could be even higher, and then only the product remains here. And what's wrong with that? And I don't have a good answer immediately. Yeah.
Okay, then let's thank Hyung Do. And there is room for more questions or comments. Yes.
Just a comment about this problem of the very different electroweak symmetry breaking pattern. I mean, this might be a problem for this kind of specific explicit constructions because it occurs at 0 temperature. But for instance, in our case, for our proposal, we studied this in detail, and we No, well, I didn't show many equations here. I mean, in the paper, of course, there are equations.
Sorry, but we are having discussions about bedtime stories. Why do you keep putting dynamics? Put dynamics in things that the thing can calculate and control of it.
We,
And then there are stuff that we don't have control of and you shove us at the right. I don't understand it.
I mean, I was saying something different. If I may first say what I was going to say, and then I'll answer to that. What I was going to say is that in constructions that use this trigger operator that occur at finite temperature, like the ones that I presented, this problem of that very different electroweak symmetry breaking pattern is not present because if the dynamics occurs at a temperature higher than the QCD phase transition, what these kind of vacua are typically absent because these vacua are generated at the QCD phase transition time. So if you have something that selects this product H1, H2 before the electroweak phase transition, this particular vacua in which H1 has a VEV that is given by the QCD condensate via the tadpole, and H2 has a big VEV, these vacua are not present altogether. This is these are the same. This is the same. I mean, this is the same anthropic argument as Weinberg's. Of course, I mean, we are going back to another topic, to the topic of before. But as far as I understand, you are just saying that universes that have not treated yet don't count in the calculation of whatever you're interested in. Now, this, you might say that this is a mild anthropic argument. And of course, this is an anthropic argument. I'm not saying not. Mild means that, mild means that in those universes have defined whatever you want. For instance, a temperature that is certainly smaller than whatever threshold you're interested in. If you wish, these universes are populated only by de Sitter entropy, which is definitely, okay, there is something, there is de Sitter entropy, but it's difficult to imagine that anything complex could be there. If you wish, define our sensor as something where matter domination could occur. In this kind of universe that have not exited eternal inflation, for sure, you cannot have matter domination. At best, you have a bath of de Sitter temperature where nothing can occur, essentially. I understand that. I'm just. I understand that. My answer to that is that our dynamics does not occur at that time. It means that what we are selecting is universes after reheating has occurred. You track the reheating surface, which is extremely complicated in an eternal inflating universe. I didn't show equations here for simplicity of presentation. No, because I mean, for our purposes, this is irrelevant in the sense that we assume just that this landscape is populated somehow. This could be eternal inflation. This could be something else if tomorrow somebody comes with something else that can populate the landscape. But this is, if you call it a problem, this is a problem that is common to all implementations of a multiverse. Okay, okay. On top of this problem, typically there is problems of infinities, in the sense that there is the so-called measure problem, that if you try to calculate that this is plugged by infinities, and this is a different story. I'm saying that among all the universes that have exited eternal inflation, only the ones surviving are the ones where the Higgs web is small. Now, in doing this calculation that we do, there is never an infinity appearing. There is never, because you assumed already that the universe has exited inflation. If you try to argue again, the other universe, the ones that stay in eternal inflation, you mean?
Okay, so let's say you can continue this line, both offline instead of only one. And is there any other question or comment, even from Zoom, maybe? Or for both talks, actually? I don't see any, so I thank both speakers again.